So today what I'm going to talk about is actually something which is somewhat older work, so in the last Prague meeting, which was now 2 years ago, I spoke a little bit about Vorob'ev's theorem, and I think I mentioned his work a little bit, and then there was some conversations that followed up from that, and then also recently other people have contextuality even and average macroscopic locality, and so the starting point for this work was actually two papers. So the two papers that are mentioned here. So one of them was about looking at average macroscopic correlations. So you have a big model and you have a macroscopic description, which is assumed in this case, in these papers, assumed to be a quantum description, and you just look at the average macroscopic correlations, and it's shown that it's local. So this is shown in this paper by Ramanathan et al. And then this other paper by Marcin and Czaslaw is about monogamy of non-locality, which is a well-known thing. But so in this paper, they derived these from just the no signaling conditions. So they looked at bipartite models or bipartite inequalities, and just assuming the no signaling condition, they derived the corresponding monogamy relation. So if you don't know what these mean, then I'll cover that throughout the talk. So sort of the point of this talk is kind of it's connecting these two results and in a small sense generalizing them, because so the first result was actually just proven for quantum models, but can be shown for any no signaling models. And similarly, the second one was shown only for bipartite, but can be extended to multipartite. But more important than that, I think, is to try to understand what is the sort of the structural explanation that's behind this. And this is related to a theorem by Vorob'ev, which kind of characterizes which are sort of the trivial scenarios. And what we will mainly, and this is what I talked about in the last Prague meeting, I think. So what we'll mainly do today is just to consider a simple example where this is shown. It's a very trivial example which can be derived very simply, like both, but the monogamy or this average thing can be derived very simply. But I think it sort of illustrates this structural explanation. And I should also mention that there's this other result which appeared more or less around that time, which is about monogamy of contextual inequalities. And so these are also derived just from the low disturbance principle. So in a sense, from sort of the contextual version of no signaling. And I'm not entirely sure what is the connection between the two, because like they seem to cover slightly different approaches. But I would be curious to understand that better, and we could discuss it later. Okay, so going to the so first just covering monogamy of non-locality. So everyone knows about non-locality. So this is sort of a usual two-party scenario of Alice and Bob. And let's consider the simplest case where Alice and Bob both have two possible measurement settings, which I'm denoting as A0, A1 for Alice and B0, B1 for Bob. And their behavior is sort of described by these joint probability distributions of obtaining outcomes X, Y, which we don't actually care. So we can assume to be just 0 and 1, but actually it's not really relevant. The outcomes are not restricted to be dichotomic. They can be anything. So the only thing that matters is really the compatibility structure of the measurements. So that's an example scenario that you can have. And usually one detects non-locality, or one detects non-locality by the violation of certain Bell inequalities, which every local realistic model must satisfy. So what is monogamy about? So the idea is, so the simplest scenario where monogamy arises, you can consider a tripartite scenario now where we have not just Alice and Bob, but Alice, Bob, and Charlie. All of them, each of them has sort of two possible measurement settings. And therefore, the probabilities, or the empirical model, is described by no signaling probabilities, which are joined for sort of choices of measurement settings for each of the parties. And now we can consider, so if we're given one such empirical model, we can consider the subsystem that's just composed only of Alice and Bob, whose probabilities you can obtain by marginalization due to no signaling. And similarly, just the subsystem consisting of Alice and Charlie. And the point, and you can look at each of these two subsystems and ask whether they violate a given Bell inequality. And the point of monogamy is that, okay, so we're looking at the same Bell inequality between Alice and Bob and between Alice and Charlie. And the point is that so Alice can only violate the inequality either with Bob or with Charlie. So if she violates it with Bob, then she can violate it with Charlie, and vice versa. And in fact, you can even say something stronger, which is that you have this monogamy relation, which is if you add up the two inequalities, then that's always satisfied, regardless of whether you have non-locality or not. And let me just clarify one thing here. So it's important to bear in mind that we have the same Bell inequality. So it's possible that Alice is non-local both with Bob and with Charlie. It's just not possible that she's non-local in sort of the same way. So the other sort of setup, which is this idea of the locality of macroscopic averages, and here the idea is the following. So let's consider a simple sort of measurement, which what we're thinking about as the microscopic measurement. So the idea is have some particle or some other system is subject to some interaction, and then we will collide with one of two detectors that says, well, okay, the measurement result was 0 or 1. So think of this as sort of a schematic thing. And this interaction is probabilistic. So you have a probability of obtaining 0 or a probability of obtaining 1. And now the macroscopic version of these, the idea is that we consider, say, a beam of particles, or you consider a region of sort of a many-speed system or something like that. And they might all be differently prepared. So there's no assumption on how they're prepared. So they can have any n particle state and correlations. And then the idea is that we're actually going to subject each of these particles to the same interaction A, and then we'll get results 0 and 1 depending for each of them. But we kind of forget about which, so we don't know which particle we're talking about. So all we have is how many particles ended up in 0 and in 1, and so we can only get the sort of these intensities of each of these beams that were splitted. And so that's all that we're allowed to have. So in a sense, there's sort of a symmetrization along these n particles, which should sort of come to the fore in what follows. And so the outcome is represented just by this intensity, and this is sort of the outcome of a macroscopic measurement. But what we care about here is actually we're only concerned about the mean or the expected value of such intensities. So we don't care about the possible fluctuations of that. And this is a way in which this is different from macroscopic locality, which, as you might know, is a system that is a principle that has been proposed to separate quantum systems from certain super quantum systems. But here, what we're talking about is just about the expected value of such intensities, and in fact, is something that will always be local, even for arbitrary no signaling systems. Okay, and so another way to interpret this mean intensity is as sort of the average behavior among these n particles. So if you'd randomly select one of the particles and subject it to the microscopic measurements, then this is sort of the outcome you'd obtain. So it's kind of, as I said, sort of symmetrizing along the n particles or the n subsystems. And now what we're actually considering is a multipartite macroscopic scenario. So we have several macroscopic sites, and they consist of a large number of microscopic sites, and one has several measurement settings at each site, or macroscopic measurement settings. So we will all subject all the microscopic sites to the same measurements. And we care about the mean value of these macroscopic intensities, and what this indicates is the behavior of a randomly chosen tuple of particles, one from each of the macroscopic sites, if you like. And this is sort of the kind of correlations that is considered in this paper by Ramanathan et al., except that they're only considering the quantum case, and here we're sort of being theory independent. And what we'll show is that as long as there are enough microscopic sites in each of these macroscopic sites, such average macroscopic behavior will always be local, regardless of what are the macroscopic correlations, as long as those are no signaling. And right, so let's see an example. And so in a sense, the reason why this is because the monogamy that we just talked about is kind of dilutes the non-locality and makes on average you see something local. So that's sort of the simple one-line explanation of what's happening. So if we look exactly at a kind of a toy example, where we have 3 sites like what we had in the setting for monogamy, and I'm choosing this deliberately so that it mirrors that exact same setting, and we're regarding B and C as forming one single macroscopic site, and on which we call M, and on the other hand, we're looking at A as forming another macroscopic site. And in a sense, in order to lump together, B and C must be of the same type. They must have the same kind of measurement setting, the same possible measurement settings. And so what we have is some symmetry that identifies the measurement settings that are available to Bob and to Charlie. And in this case, we're choosing B0 to correspond to C0, B1 to correspond to C1. And each of these gives rise to sort of macroscopic measurements M0 and M1. And therefore, if you're given a tripartite empirical model for the sites A, B, and C, then one can look at the macroscopic average behavior, which is just this bipartite model between A and M, which is this sort of this average between B and C, which is given by this average average of probabilities of these partial traced out models. Okay, so this is just an example. So with the W state and Z and X measurements, you get this. And if you do that, you actually, so Alice and Bob and Alice and Charlie actually have exactly the same so they have the same correlations between them. So that it's 2 copies of the same thing, and in fact it is local. There's another example which is actually not so it's another example where we have a tripartite model between Alice, Bob, and Charlie, and if we look at the model just at the sort of the marginalization to just Alice and Bob, we get this, which is maximally non-local. In fact, it's a PR box, and if you look between Alice and Charlie, we get something which is local, and actually very local, because it's sort of a maximally mixed model. And in fact, if we look at sort of the thing that we obtain as the average model, you can check that this is actually a local model again. So connecting these 2 things, which I guess you might have I've sort of already hinted at this connection, but the sort of general idea is the following. So if you take any bipartite Bell inequality, which is just given by some coefficients, so some linear form on the probabilities given by some coefficients, and it has some bound. And the point is that if A and M, so Alice and this sort of average thing between Bob and Charlie, satisfy this particular Bell inequality, then you can just look at that, and this is a very simple derivation, and see that this is actually equivalent to Alice being monogamous with respect, so this should be 2R, apologies for that. Alice being monogamous with respect to violating that Bell inequality with Bob and with Charlie. Right, so that's what I'm saying here. So and this is for any bipartite Bell inequality. So the average model satisfies Bell inequality if and only if the microscopic model is monogamous with respect to violating it. And in the 2 examples above, the average models were local, and or equivalently, they satisfy the monogamy relation for any Bell inequality. And in fact, this is true for any no signaling model that you might dream up on this tripartite scenario that we have under consideration with 2 measurements per site. And what we're going to look at is why this is the case, and give a structural explanation which actually generalizes well beyond this particular scenario. And this explanation is related to Vorob'ev's theorem. So before I go into that, let me just describe sort of the general setting in which we can talk about this, and this is sort of the general setting of sort of the Schiff approach, or the Abramsky-Brandenberger approach, but it doesn't really matter to follow all the details here. But the idea is that we have a measurement scenario which is determined by a finite set of measurements, possible outcomes for each measurement, although this is not really that relevant, and an abstract simplicial complex which corresponds to which is sort of the set of measurement contexts. And what it means to be an abstract simplicial complex is that, okay, so any singleton is a context, so you can perform any measurement. That's what that says. And this family of subsets is also downwards closed. What that means is that if I have a context, then any subset of that is also a context. And so you should think of a context as a set of compatible measurements, right? And this is the example of sort of the Alice-Bob scenario. we have 4 measurements, and the contexts are the things where you pick something from Alice and something from Bob. And then given that, you can, so an empirical model is just such a probability table, so it gives you a probability distribution over the joint outcomes for every context. And we assume that the generalized no signaling, or if you like, no disturbance holds, and this is just sort of that the marginals agree. Okay, so then the question one's usually interested in is in contextuality, is knowing whether such an empirical model is contextual, and that's the case when there is a distribution, a global distribution on the outcomes of all the measurements, which restricts to each of these empirically observed distribution. So contextuality sort of arises when we have a family of data which is locally consistent, in the sense, so locally here in the sense of it says that the overlaps, the margin on the overlaps, the marginals agree, so it's no signaling or no disturbance, but it's globally inconsistent, so it's contextual or non-local. Okay, so what is Vorob'ev's theorem? So Vorob'ev's theorem actually appeared in 1962 in a completely different context, in the context of game theory, and they were considered. So he was considering a collection of variables and distributions on the joint variables, on the joint values of some of these variables, and assuming that they were pairwise consistent. So the setting is very similar to the one we have. And what Vorob'ev was asking is, what are the conditions on these arrangement of variables which guarantee that there is always a global probability distribution for any prescribed pairwise consistent distribution? So for in a sense, if we translate this to our language, what this means is, what are the conditions on the measurement scenarios only, such that any model, any correlations that satisfy no signaling or no disturbance are necessarily non-contextual? And the answer he gave was a necessary and sufficient condition, which he called regularity, but which turns out to be equivalent to the notion of acyclicity, which has been considered in a database theory, and which actually has a simpler kind of description. And so going quickly through that, so the description is rather simple. So the idea is that if you have, so the idea is considered this notion of a gram reduction step. So if you have a measurement scenario, so a set of measurements and some certain subsets which are contexts, and we can delete a vertex, so we can delete a particular measurement that belongs to only one maximal context. And the simplicial complex, or this measurement scenario, is acyclic when you can follow a sequence of such gram reduction steps and sort of eliminates every measurement. So this is an example of something that's acyclic. You can look at A, it belongs only to the, so the idea here is that I'm thinking of these as, so there's 5 measurements, A, B, C, D, E, and there's 3 contexts, or 3 maximal contexts. So in particular, A, B, C, and B, C, D, and C, D, E. So these are the filled triangles here. And you can look that A belongs only to one maximal context, so we could remove that, and then we could remove E, we could remove C, we could remove D, etc., and we could sort of remove the whole thing without any problem. On the other hand, this is an example of something that's not acyclic. So here the point is that BD is a context, but BCD, the 3 of them are not a context. And here you can remove something. You can remove A, you can remove E, but here you can't remove anything because there are 3 maximal contexts, and there's no vertex that's in a single maximal context. So this is an example of something that's not acyclic. And so here's what Vorob'ev showed, is that well, sort of rewritten in our language, is that every empirical model or every correlations on a measurement scenario sigma are extendable or are non-contextual if and only if these are extendable to a global probability distribution, so they're non-contextual if and only if the simplicial complex of the scenario is acyclic, so it satisfies this Vorob'ev condition. So going back to our main problem, so let's look at the measurement scenario we're considering with Alice, Bob, and Charlie. So the idea is that we have so this D2, D2, D2 mean, so each is the part of Alice, the part of Bob, and a part of Charlie, and the point is that they have each of them has 2 possible measurement settings, and they're incompatible with each other. And this is what you can form as the simplicial complex. So you have 6 different measurements, so 2 for Alice, 2 for Bob, 2 for Charlie. And the idea is that you should think about these as sort of an octahedron where the which is hollow inside, but the faces are covered. So in particular, the measurement, the maximal measurement contexts are things like A0, B0, C0, or B0, C0, A1. So the things that pick essentially a measurement from each of so an Alice measurement, a Bob measurement, a Charlie measurement, as you'd expect in this tripartite setting. So the idea here is that, and then, okay, so if you look at this, so hidden in here is the Bell scenario between Alice and Bob, which is just this stuff that's not dotted. There's also the Bell scenario between Alice and Charlie, which is there. I looked at both of them are kind of hollow in between, so they're not acyclic. But the point is that what we're doing in taking our average is kind of looking at the symmetry that identifies Bob and Charlie, and we're collapsing along this symmetry, or taking a quotient along this symmetry. And the idea here is so erasing some of the stuff that's not really relevant for the symmetry, but the point is that when you do this collapse, even though each of the Alice Bob or the Alice Charlie scenarios is kind of hollow in between, so they're not acyclic, but when you do this collapse, you suddenly end up with a model which is acyclic. And this is sort of the macro scenario where the macroscopic correlations live, or the average correlations live. And so this is acyclic, and therefore what this means is that if we start from any no signaling model, macroscopic model for Alice, Bob, and Charlie, then the average macroscopic correlations will actually live in this quotient model, and they will necessarily therefore be local because they live in an acyclic measurement scenario. And so in particular, they satisfy any Bell inequality, and therefore, in other words, the original tripartite model satisfies the monogamy relation for any chosen bipartite Bell inequality. Okay, so I'm not sure if I have that much time, but here is an example where this doesn't work, which is if you let Bob and Charlie have 3 measurement settings instead of 2. And okay, erasing the stuff that really doesn't matter, but the point is that we're thinking of, so Alice still has 2 measurements, but Bob and Charlie both have 3 measurements. That's what's sort of depicted here. And we're still identifying sort of B0 with C0, B1 with C1, and B2 with C2. And once we do this collapse, what we end up with, and sorry, so I should have said I'm only depicting half of this, so there should be an A1 here and sort of a symmetric part of the picture there. And there's, so the scenario is built out of these 6 triangles around A. But when you do this collapse, what we end up with is sort of these 3 triangles around Alice. So there's A0, M0, M1, A0, M0, M2, and A0, M1, M2. But this is not acyclic, so you can see that none of the context belongs to a single, none of the measurements belongs to a single measurement scenario, so you can't even perform sort of the first reduction step. So more generally, if we look at general multipartite scenarios, so the idea is we have n macroscopic sites with ki measurement settings at each site I, so you can have different numbers of measurement settings on each of them. And therefore, what we're thinking about is some sort of n-partite Bell inequality on this scenario. There is a different number of measurement settings on each of these possible sites. And now we're thinking about taking Ri copies, so a number of copies at each site. We take a number of copies, or we take a number of microsites that constitute this macroscopic site, or we take a number of copies if we're thinking of it in terms of monogamy. And so we're depicting it in these ways. So, for example, A1 to AR1 are just the several copies of Alice, and we also use this M thing to sort of denote the corresponding measurement settings. And overall, sort of the scenario that we're considering is something like this. So we have R1 copies of Alice, which has K1 measurement settings, etc., up to Rn copies of sort of the nth Xavier or whatever, which has kn settings. And then the idea is that we have some symmetry that will identify the copies at each macroscopic site, and we're taking a quotient by this symmetry. And the point, and you can check that the quotient of this measurement scenario by the symmetry that we just considered will be acyclic if and only if one of the following things holds. So each of the site has at least as many microscopic sites or copies as it has measurement settings, or maybe you can allow one of the sites to have a single copy and all the others to have the exactly the same condition. And so I guess the first one is kind of more easily interpreted in terms of sort of the macroscopic averages, whereas the second one is as a clear interpretation in terms of monogamy, where you're thinking about Alice being monogamous with respect to all the others, Bobs and Charlies, etc. And you get a monogamy relation of these sort out of this. And so more generally, so in fact, this is a very general construction. We're considering the multipartite scenarios here, and this is my last slide, so getting to the end. So this is a more general construction, and the general construction is that we have these a general measurement scenario, and you can consider some symmetry given by an action of a group that identifies certain measurements. And the point is that a model will satisfy a monogamy relation with respect to these symmetry for a given Bell inequality, if and only if the macroscopic average correlations, i.e. the sort of the quotient correlations by symmetrizing along this symmetry, would satisfy that Bell inequality. So sort of the average correlations will satisfy the Bell inequality if and only if the sort of the underlying model satisfies kind of a corresponding monogamy relation for that same Bell inequality. And in particular, when this quotient scenario is acyclic, then every no signaling or no disturbance empirical, any empirical model, every empirical model that satisfies no signaling or no disturbance principles on a certain scenario sigma will be monogamous with respect to any Bell inequality. And this is because the average model, which is now defined on this quotient scenario, must necessarily be local or non-contextual, because this quotient scenario is acyclic in this case. And as I was saying, this approach is not restricted to sort of multipartite Bell type scenarios, although we sort of focus on that even on the sort of tripartite case here. But in more generally, you can apply these same ideas to derive monogamy relations for contextuality inequalities. And this is here where I'm not sure how it relates to these other approach I was mentioning, because that's also which also relates also sort of derives monogamy relations for contextuality inequalities from just a no disturbance or the no signaling principle, and it does so by relating it to chordality, which is sort of the analogous thing to acyclicity when you consider models that are just described by pairwise commutativity or pairwise compatibility. Okay, and this is all I had to say.
A question: do you know it's in a Bell type scenario, if you go to macroscopic correlations as you are considering, whether you can violate these Bell inequalities? Of course, if they are violated, your monogamy condition is saying that if one part is violating, the other, for example, Alice Bob is violating, Alice Charlie cannot violate. But if you just doing experiments, concentrating on this macroscopic data, can you really violate Bell inequalities? This is my question.
I think it depends on what you consider the macroscopic thing, but so I guess the point here is that you don't violate the macroscopic Bell inequality even in a no signaling theory. You don't even have to assume quantum theory. So in any no signaling theory, you don't violate the macroscopic Bell inequality if you're only considering sort of these average, the average of these macroscopic measurements. If you consider more than that, so if you actually have sort of the actual intensities and sort of the fluctuations of that, then it becomes possible to violate them within no signaling theories, but not within quantum theory. So this is sort of this macroscopic locality notion that's proposed by Navasquez and well, like the name has escaped me, but I can send you the link.